All right, today we're doing our notes on regression, quadratic regression. So go ahead and open your computers and log into Desmos. So you're going to need the Desmos graphing calculator to complete this today. All right, the learning target is that you can write quadratic and linear equations using regression. And you'll be able to use your calculator to find what type of regression that best fits the data given. You can also write the regression equation and then use the equation to predict values. So we use regression mostly to predict values. It's also a nice little tool to be able to plug it into the computer and find the general equation of a set of data. So our vocabulary here starts with R. This is a lowercase r. This is the correlation coefficient. Sorry, I'm already spelling that wrong. Correlation coefficient. And the correlation coefficient tells us the direction strength. Now R squared represents the coefficient of determination. Coefficient of determination. And this represents the goodness of a model. And we'll talk about that in a second. Goodness of a model. So when we talk about goodness of a model and this R squared, the R squared, the number, the closer it is to 1, the stronger the data is, and the closer the number is to 0, it's much weaker. So we'll say the closer R squared is to 1, the stronger the data is. If it is closer to 0, it is weaker. And for our fill in the blanks, it says regression is a method to find the equation that best models a set of data. We use regression to make predictions. All right, so down here a little bit lower, we have 4 different sets of data. And they're showing the different kinds of strength and different values for R squared going on here based on how strong or weak it is. And when we say strong, we're saying like the data represents a line, a good line, or a quadratic, a good looking quadratic. And so here's a good visual. The first one here is a strong positive linear equation. Notice how the data doesn't stray too far from this visual of a line. The data stays pretty tightly packed in. There's not a lot of points coming out. I mean, this little point's probably the most far out point from the rest of the data, but otherwise the data stays pretty tightly compacted along that visual line we see there. So this is a strong piece of data, and we can say that strong means tight. All the data, all the little dots are very tightly wound together. So over to the left, I'm going to say, let's predict R squared. So because the data is strong, we can say that R squared must be, is it going to be closer to 1 or closer to 0? To 1, yeah. So the data is really nice and strong, so R squared must be closer to 1. So what could we possibly estimate this as? Anyone want to take a guess? We can estimate R squared to be approximately 0.9. That's really close to 1, right? But it isn't 1. If it were 1, it would be just a straight line. A thin straight line with all of the data perfectly along that straight line. It's not perfect, so it's not 1, but it's pretty close. So we'll say the data, the R squared, the coefficient of determination could be about 0.9. All right, let's look at this next one. The one to the right, notice how the data is kind of all over the place, but it is going downward. So that would be like a negative slope. Still linear. It's not making any shape other than like a very loose line. So here the data is moderate. And another word we can use for this could be loose. So we could say that R squared, is it closer to 0 or closer to 1? Yeah, it must be closer to 0. Okay. And I mean, it's definitely not 0. We can see that it is making some sort of line. It is going in one direction, so it's not 0, but it's definitely not 0.9 like the other one was. Aiden, come on, dude. So what can we estimate R squared to be? We're estimating, so there's no right answer. I don't have the actual number to this data, so we're just guessing. Yeah, that's actually what I have written down, so good guess. That was my guess. Estimating R squared to be 0.4. Oh, I guess I should say just like I did before. R squared 0.4. Just going to separate the top two from the bottom two pieces of information. Okay, now let's look at this bottom left one. At the bottom it says null or no relationship. This is something that would be extremely, extremely, extremely close to 0. There is no general depiction of like where the dots are heading, if they're creating some form of visual that we can see here. They look like they're just completely randomized. So over here, we can say that this one, that these dots have no relationship to each other. And we can estimate this to be something like 0.000001. Very, very close to 0. Very far away from 1. All right, and then this last one, what kind of graph do we have here? It's not linear. It's a quadratic. Good. Morning. So here we have our quadratic graph. And this is actually a strong set of data. So this one, this is a negative parabola. It is upside down, so we'll make that note too. Upside down parabola means negative graph. And we can estimate, this is strong, so we want something closer to 1. Estimate r squared to be approximately maybe like 0.7. It is pretty strong, but I wouldn't say it's like 0.9 strong like the first one we had. What do y'all think? All right. So once you get this information down, you're going to go to your Desmos calculator, which is on your computer. And the steps are on the bottom of the screen here, or the bottom of your notes, really. And we're going to do the back side of the worksheet together, and then you'll do the worksheet that you picked up from the front on your own. So maybe, yeah. Can you wait till we're done with the notes? Thank you. All right, I'm going to pull up my Desmos calculator as well. All right, so here's my Desmos. All right. So the first step says to click on the plus sign and select table. Then it says enter the data. So turn to the back of your worksheet. And typically when we have a table of data that's going to the left, from left to right, Julian, can you pick your head up, please? Join us. On the top one, it's usually X, and on the bottom one, it's Y. So let's go ahead and enter all of the X data on the left column and then all of the Y data on the right column. So here we have 7, 15, 17, 23, 27, 33, 38, 43. All right, once you get your graph or your table data plotted, the next set of instructions says click on a new cell. So we're going to click on the one that says 2. And it says for quadratic regression, enter the equation y1 squiggly, that's called a tilde, ax squared with the 1 subscript plus bx1 plus c. Okay, yeah. So we're going to type in the quadratic one and then go into a new box and type the linear one. Those are both listed on your directions on the notes. Can I not see this here? Okay, that's fine. I'll just type y1 squiggly there it is, ax1 oops, okay. Oops. ax1 squared plus bx1 c y squiggly x1 plus b. Oh, right. y1. Okay. Is anyone having trouble typing in the equations? Yeah. Anyone else need help? Good? Okay. All right, so once you get your quadratic regression entered and the linear regression entered, so here I have my quadratic y1 tilde ax1 squared plus bx1 plus c, and then your linear one, y1 tilde mx1 plus b. All right, once you get those entered, we are going to look at the data. So it says to list the linear r squared. What does your linear r squared there say? Your r squared says 0.1? Oh, okay. Mine says 0.83. Does anyone else say something different? Raise your hand if yours says 0.81. Raise your hand if yours says 0.83. Oh, you're looking at the linear one. Yeah, we want to look at the one with the quadratic, the one with the 2. Okay. So here we're going to say 0.83. Oh, that is the linear. I see why we were, okay, my bad. Linear does say 0.81, and then the quadratic does say 0.83. Awesome, okay. Now for the equation, we need to look at the A, B, and C for the quadratic, and then the M and B for the linear. So here, okay, so I'm gonna write the quadratic one on top. So using that formula, we have ax squared. Our a value is 0.0076. 0.0076 x squared plus bx. B is 0.168. We'll round it to 2, x. And then plus your c value. So there's our quadratic equation. And then we can also write the linear equation right below it. M is 0.5529 x plus b 52.7902. Okay. Now let's take a look at the data and determine which one of these equations is going to be more accurate for this set of data. What do y'all think? Do you think the linear graph works better for the set of data or the quadratic? Kind of hard to say, right? It seems like it's curving, If we omit this dot right here, it does seem like it curves, but the linear data with this dot here kind of brings it back this way. So I'm going to go with the quadratic graph. I think that one would be better. Plus, if we look at the y values, they are increasing, but some of them go down. I think the quadratic graph would be better, just because it's curved a little bit. Plus, we are in the quadratics unit, so that's kind of a hint there. Okay, it says predict the test score of a student who studies for 60 minutes. Okay, so 60 minutes, the time was the x value. So how can we predict the test score for 60 minutes? What should we look at on the graph? If x is 60, shouldn't we just look at x when it's 60? Right? Yeah, so let's look at 60 for x. And that looks like with the quadratic, it would be about right here, which is 2, 4, 6, 8. Looks like about 94. I think we can also, I'm not so great with Desmos, but I think we can also type in here x equals 60, and you can see what the value is at that point. Okay, so when x equals 60, on the quadratic graph, it says our y value is 94.1141. So the test score of a student who studies for 60 minutes, we can say, I'm going to cross out this one. We can say x equals 60, y equals 94.1141. And so that means that's what they would get on their test. If they studied for 1 hour, they would get a 60 on their test, or a 94 on their test. The next one says, how much should a student who scored a 72 have studied for the test? How much would they have studied? So what value is the test score, x or y? Y. So let's look at the y value of 72. So now we can say y equals 72. Look at the quadratic for that point. And it says when y is 72, x is 34.746. So it seems that they only studied for approximately 35 minutes. That was the regression that we typed in. When you type this in, it'll draw a line there for you, given the table that you typed in. Okay. Let's go ahead and exit out all this data that we've entered, and let's do it again for the next example. All right, this one says, this data table shows the per capita consumption of broccoli, B, in pounds for the years 1980 through 1989. Let T represent the year with T equals 0 corresponding to 1980. So they're saying that year 0 is 1980. So let's take a look here. If year 0 is 1980, that means 1981 is year 1 and 2 and 3 and so on. So in our calculator, we're not going to be typing in 1980, 1981, 1982 as our y values. Let's just use 0 through 9. It'll make this graphing much easier. Okay. So let's go ahead and type in this data into the Desmos calculator. In a table, just like we did before. So you'll hit the plus, and then you'll hit table, and then we'll just start with the x values being 0 through 9. That's nice. Once you get all of your data entered, then you'll type in the regression equations for both, which are again on the front page of your notes. And the little subscript of 1 that you're typing in, I just put y and then I hit 1 and it automatically goes below. For the 2, for the squared, you need to hit Shift 6 for that little caret, that little up arrow. Now, once you get all of your data posted and the 2 regression equations, you can look at the data. And if I hit that little colored in dot on the linear equation, you can see that the data very nicely follows along the curve of the quadratic. So this one is going to be the quadratic equation. Now our linear r squared is going to be the number that's listed there, which is 0.9839. And the quadratic r squared is 0.9916. Then you'll write the equation of the one you choose. You don't have to write both, just do the one you choose. So we'll have y equals 0.0113, oh, I guess 4. Bye guys, have a good day. Y equals 0.0114 x squared plus 0.2231 2x plus c 1.6018. There we go. And then we can type in, or not type in, but answer the last question. In which year was the per capita consumption of broccoli 5 pounds? It says 10 years. Oh, just kidding. Don't answer that. In which year was the per capita consumption of broccoli 5 pounds? So then we'll go to our graph, and we're going to type in pounds. That was the y. So we're going to say y equals 5. Look at the point there. And it says 10 years. Then the last questions, oh, again, so this is when y equals 5. What would the per capita of broccoli be in 2005? Well, 2005 would be, the 9th year is 1989, so 2005 would be the 14th year. Oh, wow, I'm counting so wrong. Okay. 2005 minus 1989, that's going to give us 90.05. That's, why do I say 25 years? Is that really 25 years? 5? Oh, I see what I'm doing wrong. Okay, no. Sorry, guys. 2005 minus the original year, 1980. That's 25 years. So we're looking for x equals 25. There we go. Where's that point? Okay, so when x equals 25, our y value is 14.14. So oh, am I looking at the wrong point? 14.28. pounds. Awesome. So that concludes our notes for the day. Go ahead and get started on the assignment. All right, that's it.